So about cycles, um, if you have a even cycle, it turns out you can always color it with two colors. Okay, so and it's probably not that hard to see. What you could do is that for all वर्डसीज को लेबल कर लें. Okay, for all vertices with odd indices should get, for
Yeah, bro.
example, red. Okay, and for all vertices with even indices should get, I don't know,
So isn't
yellow.
this very similar to the partition problem? ये bipartite है तो दो sections.
Absolutely, really good. Yeah, yeah, yeah. Actually, we sort of touched it before. So these are um, C even, yeah, cycles on even nodes are two colorable because these graphs are actually bipartite. Okay, and bipartite graphs are the only graphs which can be colored with two colors. Okay, you get two partitions. उन partitions में कोई within edge नहीं है, तो इसका मतलब ये है कि you can give it one color and the other partition the other color, and these are two colorable. Okay, and whenever you have a two colorable graph, you can consider these two partitions for it. Okay, so this sort of clearly defines the family of graph which are two colorable. Okay, every two colorable graph must be bipartite graph, and every bipartite graph can be two colors. Okay, so this is the full characterization of all the graphs which can be two colored. All right, I hope everyone sees it. If you don't, now is the time to raise your voice. Um, about the cycles which have odd length, you actually do need three colors, and that can be seen from, for example, this example. और हमने इसको पहले भी discuss किया था कि if you have an odd colored graph, odd length graph, then you can't use two colors. Okay, because then you would have a problem with the first vertex and the last vertex. यहाँ पे आपको problem आ जाएगा. Okay, but you can color it with three colors. You just need to use a different color for the kth vertex. Okay. Now comes a question before I move on, and the question is, what sort of graphs are three colorable? Okay, so for two colorable graph, we have absolute characterization that these must be bipartite graph. You give me a graph, I'll try to figure out कि ये bipartite है या नहीं है. I can do it simply by, ये जो coloring वाला procedure था, I can start in arbitrary vertex, give it a color, उसके neighbors को different color दूंगा, उसके neighbors को different color दूंगा, and continue until either I color the graph with two colors, or I reach a vertex which can't be colored, either yellow or red. Okay, so two colored graphs are absolutely characterizable. बहुत आसानी से मैं find out कर सकता हूँ कि ये graph two colorable है या नहीं है. How do I figure out whether a graph is three colorable or not? What do you guys think? I don't know about you, but the thing is, the answer to this question is no one knows up till this point. Okay, so this is an unsolved problem, and no one knows how to figure out whether a graph is three colorable or not. Okay, so if I give you a reasonable, मेरा ख्याल है 5-10 nodes तक तो आप सारी combinations try करके बता देंगे. लेकिन if I give you a graph which is more than, for example, 25-30 nodes, you would be really pushed to the wall. You won't be able to tell me whether the graph is three colorable or not. Okay, so it's a really hard problem to find out whether a graph is three colorable or not. Okay, and this is already, this is just three, right? If I go to 4, it becomes harder. But it's sort of humbling. Even for three colors, you can't find out whether you can color a graph with three colors or not. All right, move on to the next category, which is the complete graph. Complete graph may You need n
Sir,
colors.
तो
We go there.
how did we know for the USA वाला graph के इधर कितने colors होंगे if we can't even do it
Oh,
with
we'll talk about it. We'll talk about it. Okay. This is a special graph, and we'll figure it out. Okay, how do we find colors, the minimum number of colors that we need for this graph? Okay, good question. So I'll come back to it. So for the complete graph, you need n colors. You can't do it with n minus 1 colors. You need a different color for every vertex because, and here I pause for someone else to.
Because every node is connected to other.
Yeah. So every node is connected to every other node, which means कि किसी भी दो vertices के लिए I can't use the same color because they have an edge between them. Okay, good point. ये कौन था?
RNS.
Anas, okay, good. Yeah, so you need a different color for every vertex because you can't use one color for two different vertices because every pair of vertices is connected by an edge. और proper coloring के लिए हमने कहा था कि you must use different color for two endpoints of each edge. Great. यहाँ पे एक छोटा सा comment है before I move on to the new category of graph. वही है कि if I give you a graph जिसके अंदर एक there is a vertex, let's call it the max degree vertex, okay? इस graph में ये जो भी graph है उसके अंदर this is the max degree vertex, okay? इसकी degree maximum है. I know that I can color this graph with this many colors. And how do I know this? So let's say this is a graph जिसके अंदर जो maximum degree है किसी node की वो 4 है. Okay, and I'm claiming that 4 colors are enough to color. Sorry. What do I want to say? I want to say that 5 colors are enough. Okay, degree plus 1 colors are enough. So chi of g is less than or equal to delta plus 1. How do I know this?
One color is needed for the node itself, which has
Yes.
degree of 4, and then
Yeah.
4 other colors for the other nodes that it is connected to. So that makes 5
Yes.
colors.
Yes. So what I know is that I can color this vertex with one color. I don't know, whatever that color is. And then I would have left 4 colors, which I can use on these vertices. But I would have sort of some problem in the sense that I don't know कि बाकी nodes का color कैसे होगा. Okay? तो इसका जो actual logical solution है वो by induction है. Okay? You go to a vertex which has the maximum degree. Okay? और फिर ऐसे करें कि आप बाकी ग्राफ को कलर कर लें. Okay, so this is the logical reason that you need to prove that chi of g is less than or equal to delta plus 1. That you forget about this vertex which has degree 4 and you color the rest of the graph. ये जो g bar है इसको color कर लें by induction. By induction you can color it with 4 vertices, 4 colors, right? अब इसको color कर लिया, sorry 5 colors, okay? इसको color कर लिया तो यहाँ पे इन 4 nodes के लिए you must have used at most 4 colors, right? There are 4 vertices, so you must have used at most 4 colors, which means that there is 1 color left for this guy. Okay, whichever that thing is. Okay, so you have a color for this guy, and you do this. So if the degree of a node is delta, okay, maximum degree of a graph is delta, so you can use delta plus 1 colors to color that graph. Can you do better? The question is, can you do better? The thing is, you need 5th color whenever these 4 vertices have different colors, right? अगर इन दोनों में से कहीं पे भी कोई 2 vertices हैं जिनका कलर सेम है तो फिर मुझे 5वां कलर जरूरत नहीं है उसकी, right? I can use the 4th color. So
Yes.
let me, I don't know if I can. So for example, this guy is green, this guy is black, and this guy is pink. Ab, if this guy is green as well, तो फिर I am still left with the 4th color. मैंने 3 color use किए इसकी neighborhood में. which means I can use the fourth color to color this node. Okay? To make sure that I can't use the fourth color, I have to assume कि ये सारे के सारे आपस में connected हैं. Yes? अगर ये आपस में connected हैं तो फिर I can't use the color the same color again. Okay? So इस तरह का जो ग्राफ है वो complete ग्राफ होता है, जिसमें you pick a vertex, उसकी जो neighborhood है वो आपस में completely connected है, फिर उस vertex की neighborhood आपस में completely connected है. So it looks like कि if it's not a complete graph, chi of g might be less than equal to delta. But let me give you another example जिसमें ऐसा नहीं है. How about this graph? How many verses did I make? 1, 2, 3, 4, 5. I need 2 more. 6 and 7. What's the max degree? And how many colors do I need? 3, right? I need 3 colors because it's an odd cycle, right? It's not a biverted graph. So इसका मतलब ये है कि complete graph is not the only graph which requires delta plus 1 colors. Okay? Even for odd cycles, you need delta plus 1 colors. Okay? But there is a famous theorem. It's called Brooks' theorem. You should, if you find yourself enticed by this problem, you should look it up. It's called Brooks' theorem. It says that that's it. That's it. These are the only 2 examples where you need delta plus 1 colors. Okay. One example is this complete graph. The other example is an odd cycle. इसके अलावा every graph can be colored with delta colors. Okay. I'm not giving you any hint for how it works or सारा कुछ, but I'm leaving it here. This to me is very surprising. Okay, a professor told me this thing in I think 2012 or 2013, and I was wow, right? These are 2 examples, an odd cycle and a complete graph where you need delta plus 1 colors, and that's it. Any other graph in the world can be colored with only delta colors. Okay, so that sort of, I still find it very interesting. Anyhow, okay, so this graph is called a wheel graph. What is a wheel graph? Wheel graph is a star graph. Star graph is a vertex which is connected to a bunch of vertices. None of them are connected. Okay, and a wheel graph is a star graph plus this cycle. Okay, which makes it this thing. Okay, so you have a star in the center, and then you have a cycle in the outer, okay, in the belt. Okay, so so the statement says that if your wheel is on odd vertices, और उसकी जो length है वो odd है. अब यहाँ पे जो odd है, this is actually the what is it? I think it's the
outer cycle.
So
yeah.
odd is the outer cycle.
Yeah,
Isn't
yeah,
it?
yeah. So it's the length of the outer cycle, I think. Let me just make sure, okay? So that there are no dot slats. How many colors do we need for this? So you need a different color for this guy, okay? And then you will need a color for this, okay? Yeah. So odd is the length of the outer cycle, okay? Because you can color this with 3 colors, right? So 1, 2, 3, 2, 3. Yeah, you can color it with 3. Okay, so if the outer cycle is of odd length, you need 4 colors. Okay, 3 colors for the cycle and the 4th for the central vertex. If it's even, 3 colors are enough, and 3 colors are needed as well. Okay, you can't do less than 3. You need exactly 3. How about trees? What do you guys think? How many
Sir,
colors do you
can
need?
you define first what a tree is?
Okay, sure. A tree is, मेरे ख्याल में हमने इसको define किया पहले, but a tree is a connected forest. Okay, और forest हमने define किया था, it's an acyclic graph. Okay, So a tree is a connected graph without any cycles. Okay, so this graph must be connected, but it must not have any cycles. So how many colors do you need for tree?
2.
Yeah, 2 is enough, and it's not that hard to see. You start with an arbitrary vertex, कोई भी एक vertex पकड़ लें, उसका कलर रेड कर दें, उसके जितने भी नेबर्स हैं उनका कलर ग्रीन कर दें. ओके, अब इनके जो नेबर्स हैं उन सब का कलर रेड कर दें, एंड देन यू रिपीट. Since there are no cycles, you will never have a conflict. You can always color the next vertex with a different color. And you need 2 colors because there's an edge, right? Wherever there's an edge, you must need 2 colors, okay? You can't do less than 2, but 2 is enough because there are no cycles. Awesome, great. So trees only need 2 colors. And even cycles need 2 colors, okay? A triangle is not 2 colorable and odd cycle is not 2 colorable. We know about biverted graph already, so let me skip this part. So this thing I told you, okay? What sort of graphs are 3 colorable? No one knows. General characterization. No one has an algorithm and no one has a sort of mathematical proof कि किस तरह के ग्राफ होते हैं जो 3 colorable होते हैं.